We're going to try and solve several inequalities at once now to find a region on the graph which satisfies all three of these inequalities. In order to do that, I'm going to sketch them one by one. So I start off with a nice big set of axes. Do not try and squeeze your sketches in a small little gap. Bigger sketches allow you more space to see what you're actually doing. So I'm just going to, for a moment, imagine that this were an equal sign and sketch the line y equals 3x plus 4y equals 24. The best way to sketch that line is to just find your x and y intercepts and join them with a straight line. So let's do the y-intercept first. To find a y-intercept, I set x to 0, and I'm going to get 4y is less or equal to, because I'm imagining it's equal to 24. That would give me y is 6. I then do the same for the x-intercept. Imagine that y is 0, and I'm going to get 3x is less than 24, which gives me x is 8. You see, because it's a sketch, I'm not worrying too much about my scale. It's roughly correct, and that's all we really need. Okay, and now what I'm going to do is join these up with a nice straight dotted line. I'm using a dotted line as I have a strict inequality. Y is less than 24, or 3x plus 4y is strictly less than 24, so I know I cannot actually be on that line. Okay, the next one, x is greater than 0. That would lie on the y-axis. So I can sketch that line on. Again, a dotted line, because I can go up to, but not quite be on that line. Whilst we're at it, let's just label this one so that we don't forget. And now finally, we have a quadratic that we need to sketch. Sketching quadratics made much easier if they factorise. So let's just have a quick look and see if this factorises. Factors of 16, which can add together to give 6. That will work if we have x and an 8 and an x and a 2. I know that one must be positive and one must be negative. Negative 8 plus positive 2 does give me negative 6. That's factorised. I have an x-intercept of 8 and another x-intercept at minus 2. So if we just sketch that on, again, it's the shape that's important, not all of the exact values. As long as we make sure that if they both pass through 8, they pass through the same point on the x-axis. Okay, and you see I've used a solid line because it can equal that value. Okay, so dotted lines for strict inequalities. If it's less than or greater than or and equal to, then you use a solid line. Now I need to figure out which region it is that I'm actually interested in. You will often be asked to shade the region that satisfies all of these inequalities. I find it easiest to consider the y, because then if I know that y has an upper limit on it, in this case y must be less than 24, I know that I can shade the region below that line. Y must be less than it, lesser values are below. You can consider the x and think left for less, right for more, but people just seem to find the y more intuitive for some reason. Here, x is greater than 0, we need the positive values. Greater than, we're going to the right. And then here, y is greater than this quadratic. So again, I want the region above the curve. So if I shade the region which satisfies all of those, I need it below this line, to the right of this line, and above the quadratic. The only region which satisfies all of those constraints is that region there. You see, I've got a nice big sketch so that I've got room to fit everything I need on. I've labelled what I'm doing, he says, realising that he hasn't in fact labelled this one. So that I can keep track of everything, and then I just look at each of my inequalities in turn and think, do I want the region above or below the line?